time for your class.
Yep. All right, it's 8 o'clock and I see as normal that Alex is here and the rest will show up here and there. Maybe we'll get lucky and one day Dugan will come. All right, antiparticles was the last thing we talked about. You can be antiparticle all you want, but they still exist. Wavicles, as mentioned when we brought this term up under electrons. It's a made-up word, makes sense. Wave-like, wave-ical, wave and particle-like. They carry forces. That's how forces are thought to be carried. And I suppose there is at least some amount of physical evidence for at least some of these. So photons are, of course, light. And light is an electromagnetic wave. So they carry the electromagnetic force. And light is like electrons in that, of course, well, we're talking about wavicles, so they're all, of course, they're the same. But that's one of the freaky things about light is that particles and waves aren't supposed to, they're supposed to be mutually exclusive. I mentioned to you when we were talking about, let's see, reflection, refraction, diffraction, that one of the unique properties of waves is that it, a wave, when it hits a small opening, does not just go straight through like a particle would. Particle would either hit the opening and go straight through, or it would not hit the opening and it would be reflected back. Waves are reflected back, but waves on the edge bend around so that the new wave that comes through the opening looks curved like the original wave did. And that's supposed to be one of the unique properties of waves. Well, light does that, so it's a wave. But light can, for example, push a solar sail, so it's a particle. For a while, I guess it's my understanding scientists struggled with that because they were supposed to be mutually exclusive. Either it was a wave or it was a particle. So photons, visible light is what we normally think of, but if I understand correctly, any electromagnetic wave is carried on a photon. They carry the electromagnetic force. Gluons, I think this is a hilarious word, gluons, they make things stick together, carry the strong force. And remember, the strong force is what holds nuclei together. It is 100 times stronger than the electromagnetic. Just a minute. Sure wish I could figure out what setting was different in this new version of Word that made it do that. What it's doing, if you haven't noticed, is it's jumping to wherever the cursor happens to be. So gluons, if you remember, are 100 times, the strong force carried by gluons is 100 times stronger than the electromagnetic force. The electromagnetic force is the force that holds electrons on the in the atom and that tries to repel the nucleus apart. Weak bosons, that's a funny word to me, carry the weak force. The weak force holds what? I think it's protons and neutrons together. And gravitrons, yes, gravitrons, not to be confused with the ride at the fair. But gravitons are the wavicles that are thought to carry gravity. So if you remember, there are 4 fundamental forces that hold the universe together, and we can't explain any of them, which, as I believe I mentioned back when, at the beginning of the year, I find that very interesting, given the verse in the Bible that says that God created all things, and by him all things consist. And the Greek word that was translated consist means are held together. So to some degree, we have evidence for these particles. For some, maybe not so much. One way or another, it's God holding everything together. Now, that brings us to the end of not all, but all of the more important, more common elementary particles. And now I want to spend some time talking about actually using the nucleus. So a nucleus contains less energy than the nucleons that make it up would if they were separate. Remember, a nucleon is a particle in the nucleus. That is, it is a proton or a neutron. So the simplest common atom that we can, the simplest common atom, bigger than 1, bigger than just a proton, is helium. So that's why we've got helium coming up down here as an example. We'll get down to it. Nucleus contains less energy than the nucleons would if they were separate. So in other words, helium, 2 protons, 2 neutrons. If I had 2 random protons floating around, or 2 random neutrons floating around. And by the way, they would not float around forever. They would find a nucleus to become part of, or the protons would find some electrons, but they can't float around forever. But if I had 2 protons and 2 neutrons floating around, matter is made of energy. They would have a specific amount of energy. When I put them together to make helium, there's still a specific amount of energy, but it's not the same as just adding up the energy of the parts. We'll get there. So the difference between the energy of a nucleus and the energy of its individual components is called the binding energy. Binding energy is always negative because the nucleus has less energy than its parts would have collectively if they were separate. So in nuclear physics, energy changes results in mass changes. So in nuclear physics, and that's the E equals mc squared. So in nuclear physics, if we weigh the particles, which is easier said than done, I grant you, but if we weigh the particles, their weight corresponds directly to how much energy they contain. So 2 protons and 2 neutrons. Remember, that's what makes up a helium nuclei. 2 protons and 2 neutrons individually. In other words, a proton, P, and a proton, P, and a neutron, N, and another neutron someplace else. If I weighed these 2 protons and these 2 neutrons, they would weigh 4.32980 U. U is the atomic mass unit, incredibly tiny. So 4.032980 if they were floating around independently. If I take these same, okay, there it is still. Let's see, get my pen back. 4.03298. If I put these 4 particles together, 2 protons and 2 neutrons, into a helium nucleus, still 2 protons, 2 neutrons, that helium nucleus would have a mass of 4.002603. In other words, not much, but definitely less than when the pieces were floating around by themselves. And that difference is referred to as the binding energy. Although it may not, binding energy may not be expressed in U in atomic mass units. The difference is referred to also as the mass defect. So the difference in mass, in case you didn't want to put it down in your, take the time to punch it into your calculator, the difference between those 2 numbers is 0.0030377 atomic mass units. That difference is lost energy. So if I had my 4 pieces floating around, 2 protons, 2 neutrons, if they came close enough, within 1 or 2 femtometers of each other to be attracted by the strong force, and whoom, they attracted together into the nucleus, they would give off energy. It would lose mass in the form of energy, and frankly, that's the kind of thing that drives suns. So the difference in mass between a nucleus and the total mass of its parts is the mass defect. Now, notice this. As a general rule, the larger a nucleus, the more tightly bound its nucleons will be, and the larger its mass defect or binding energy. So, helium, smallest nucleus that's not just 1 proton. So that has a mass defect of 0.00303777. Let's say oxygen, number 8, has an even larger mass defect, and its nucleus will be more tightly bound than helium's. Or let's say sodium, I forget, 17 or 18, somewhere in there, I think. Sodium has an even larger mass defect than oxygen, and its nucleus will be even more tightly bound together than oxygen. This rule, that is, the larger nucleus, the more tightly bound its nucleons, applies up to, now this is an important isotope to remember. This rule applies up to iron 56. Above iron 56, binding energy decreases. So if you start with helium, you have a reasonably stable nucleus. Let's see. Next after helium would be lithium, number 3 on the periodic table. Has a little bit more stable nucleus. And then hydrogen, helium, lithium, beryllium would be the next one. And what, maybe aluminum, I think. Aluminum doesn't seem right, but maybe it is. Anyway, each of these as you go up has a larger nucleus. Up until you, yes, of course larger, but a more stable nucleus. Up until you hit iron 56. After you hit iron 56, the bigger the nucleus becomes, the less stable it is. The more easily it can be knocked apart, split, whatever the case may be. So that's why iron 56 is an important isotope to remember. That is the line between, that's the line after you cross it that nuclei start to get less and less stable. So, nuclear reactions occur naturally if the reaction results in a nucleus with a more negative binding energy. In other words, just like everything else, reactions that tend to give off energy are favorable, and reactions that require an input of energy are not favorable. We're still talking about laws of thermodynamics here. So large nuclei tend to decay into smaller nuclei. That's why the alpha, beta, and gamma radiation that we talked about a couple of days ago, that's why the elements that give off those kinds of radiation are the very large nuclei. So larger nuclei decay into smaller nuclei. Larger nuclei decay into smaller nuclei. Above, there it is again, iron 56. Large nuclei have more negative binding energies. So, okay, it starts becoming important to notice these numbers. So uranium-238, other forms of uranium too, but we're going to look at uranium-238 right now. Ejects an alpha particle. If you remember, an alpha particle is a helium nucleus, 2 protons and 2 neutrons. So that would be an atomic mass of 4. So if you have 238 and you lose 4, that takes you down to 234 right there. And thorium, there's, okay, careful. This was 4 protons plus neutrons, but that's only 2 neutrons and 2 protons. So thorium is 2 atomic numbers smaller than uranium. If you have a periodic table, you can glance at right now. This makes perhaps a little more sense. Thorium-234 has a more negative binding energy than uranium-238, because remember, the closer we get to 56, the more negative the binding energy. So the process releases energy and is thermodynamically favorable, likely to happen. Now, don't be confused. Likely to happen does not mean it happens all at once, kaboom. It means that over time, sooner or later, it is probably going to happen spontaneously. So if we had all of the time in the universe or world, or however you want to put it, if we had billions of years to watch this experiment, we could make, and we don't obviously, but we could make a pellet of pure uranium-238. And if we came back in a billion years, I don't know the half-life, I'd have to look it up, but a lot of that uranium-238 would have given off alpha particles and changed into thorium, and a lot of the thorium would have changed into whatever it changes to. So it doesn't happen fast, doesn't happen but it does happen spontaneously on a random basis. You never know which uranium's going to lose an alpha particle next, but it does happen. It happens naturally, unstoppably. It happens. Now, smaller nuclei don't decay because they become more stable up until iron 56. So below that iron 56, larger nuclei have less binding energy, and this is the fuel for the stars. Pen. Nuclear fusion. Fusion is the smaller nuclei fusing into larger nuclei, is the fuel for stars. It's what runs the sun. It is a cleaner process, better process for making energy than nuclear fission is. If we could figure out how in the world to use nuclear fusion to our advantage, we would solve all of the energy efficiently and safely, use it to our advantage. We would solve all of the energy needs of the world, and pollution would become a thing of the past to a large degree, seeing as how most pollution is the result of energy conversions, directly or indirectly. But so far we haven't been able to do that, so we're just kind of out of luck. Any questions so far? All righty. Artificial radioactivity. Now, we talked about natural radioactivity, alpha, beta, and gamma decay. Back in the, I suppose it would be 1800s, we started to learn about radiation, and we didn't really know what it was. As I recall, if I remember correctly, we discovered it by accident. Someone, and I think it might have been Pierre Curie, was studying, I think it was uranium, and stuck a rock, a uranium rock, in a desk drawer, and don't know exactly all the details. Now, this is before film, as digital for sure, and film on plastic sheets, as you may know it. This would have been in a day when film was a paste painted onto a glass plate. You've seen maybe the old pictures of the big old camera with the hood and the flash pan and a big old plate that slides in. That plate had the film chemicals painted onto glass. And I think it was Pierre Curie, but I may be getting my stories mixed up. Put some uranium in with in a desk drawer with a photographic plate, And later he discovered that the photographic plate in a closed drawer had been exposed. And that's how they found some kind of radioactivity anyway. And then Marie and Pierre Curie, and this was a French couple, married couple, found that substances placed close to radioactive uranium became radioactive. So if they put aluminum next to uranium, which is, remember, giving off, that should be He, giving off a alpha particle, that aluminum changed into phosphorus and gave off a free neutron. Okay, the free neutron is the radiation there that the radioactive phosphorus is giving off. Also gave off a positively charged electron, but they didn't know that at that time. So back when we're discovering these things, we don't understand anything about radioactivity. We don't know about protecting ourselves. We don't know it's deadly. We don't know it causes cancer and all kinds of other diseases, and can affect bone strength and can affect healing ability. So we were just, we humans who studied these things back then were just cavalierly playing around in their laboratory with their traditional lab coat and probably not even goggles on. And so Pierre Curie died of radiation exposure. His wife Marie kept on the research, and so actually Marie Curie is probably ended up doing a lot more than her husband did. Somewhere, I haven't thought about this for a while. Somewhere I've got a book on her. I don't remember where it is. Okay, so positrons were discovered by Carl Anderson. At the time, Pierre and Marie are doing these things, they do not realize about the positron. So radioactive isotopes, and we use radioactive isotopes for all kinds of things these days. Radioactive isotopes can be produced by bombarding stable isotopes with any type of nuclear radiation. So let's say they want to, let's say you have thyroid cancer, hopefully not, I mean, just hypothetically speaking here, hope you never get it. But thyroid cancer is one of the easier ones to treat because of what I'm about to tell you. So let's say you get thyroid cancer. Well, the thyroid takes all of the iodine out of your system and hoards the iodine. It needs it to make its hormone. So if you get thyroid cancer, they can expose some iodine to radiation and make it radioactive and give you that radioactive iodine, and it will accumulate in your thyroid and radiate the radiation directly into the cancer. Or let's say that they want to take a picture of your digestive tract with a X-ray. Well, let's say you've got a potential obstruction or something in your small intestine. So they, soft tissue like a small intestine doesn't show up very well on an X-ray. I mean, if you've seen an X-ray of your abdomen, you can make out where the intestines and so on are, but it's not super clear. Soft tissue just doesn't give a good picture for an X-ray. So they can give you a drink of something that's got a mildly radioactive isotope in it and give that a chance to go through your intestine, and then your whole intestine will give off not light that you can see, but light that will expose an X-ray, and they can tell where the obstruction might be, for example. So we've got all of these different uses for all of these different radioactive isotopes. And so this is pretty important technology. Newly formed radioactive isotopes will remain radioactive until the nuclei have all transmuted or changed into stable isotopes. And we use that to our advantage also. So, you know, you need a X-ray of your digestive tract. You want a little bit of radioactivity for a short period of time. You don't want your digestive tract to be glowing for the rest of your life. So they may make a isotope that has a half-life of just a few hours, so that within a couple of days it's all changed into stable isotopes and it's no longer radioactive. Or if you're getting cancer treatment, they may want that iodine to stay radioactive in your thyroid for, I'm just guessing here, maybe a month. So maybe they make an isotope that is radioactive, has a longer half-life, and will stay radioactive in your thyroid for a month. And the numbers I just pulled out of the air for illustration purposes, but with practice, we've learned what element bombarded by what kind of radiation makes these different kinds of elements. All right, that's all I'm going to do for today. We'll pick up with nuclear fission tomorrow. And tomorrow we'll finish the week. You do have a quiz open to you now. So please make sure that you get that done by 3 o'clock. Other than that, does anyone have any questions? All right then, I will let you go and have a good day.